Welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 203, titled Remove Linked List Elements. This problem is a great opportunity to practice working with linked lists and learn strategies for efficiently modifying them. Let's dive in and explore the solution. In this problem, you are given the head of a linked list and an integer val. Your task is to remove all nodes in the linked list where the node's value is equal to val. Once you've removed these nodes, you need to return the new head of the linked list. For example, in the first example, the input linked list is 1, 2, 6, 3, 4, 5, 6, and the value to remove is 6. Here, all nodes with the value 6 are removed, leaving us with the list 1, 2, 3, 4, 5. This is the resulting linked list that we return as the output. Now let's look at another example. Here, the input linked list is empty, meaning there are no nodes, and the value to remove is 1. Since the list is already empty, there are no nodes to remove, so the output is simply an empty list as well. In the third example, the input linked list contains 4 nodes, all having the value 7. The value to remove is also 7. Since every node matches the value, all nodes are removed, which results in an empty list as the output. This demonstrates the case where the entire list is cleared because every node matches the removal condition. Let's break this down further with some additional details. In the third example, all nodes had the value 7, which matched the value val we were asked to remove. This is why the final output was an empty list, as there were no nodes left after the removal process. Moving on to the constraints, the number of nodes in the list can range from 0 to 10⁻4. Each node value, as well as the value val, falls within the range of -10⁻5 to 10⁻5. These constraints ensure that the problem can handle both small and large inputs, so your solution needs to account for efficiency when dealing with potentially thousands of nodes. Now let's consider some important edge cases. First, if the input list is empty, the output should also be empty, as seen earlier. Second, if no node in the list has a value equal to val, the output should simply be the original list, unchanged. Third, if every node in the list matches the value val, the result will be an empty list. Fourth, if the list contains only a single node and that node matches val, the output should also be an empty list. Lastly, when there are consecutive nodes with a value equal to val, all of them should be removed while maintaining the order of the remaining nodes. These edge cases help ensure that our solution is robust and handles all possible scenarios correctly. To solve LeetCode problem number 203, we need to remove all nodes in a linked list whose values equal a given integer, val. The key challenge here is to modify the list in place and return the updated head. One approach we can consider is a brute force method that rebuilds the list from scratch. The idea is simple: we traverse the original list and append only the nodes that do not match the target value val to a new list. This way, the new list contains all the original nodes except the ones we want to remove. The process involves iterating through the linked list, checking each node's value, and skipping nodes with values equal to val. While this approach works in linear time, it has a significant drawback: it requires additional memory to construct a new list, making it inefficient for scenarios where in-place modification is required. This trade-off between simplicity and memory usage highlights the need for a more space-efficient solution. Now, let's examine an iterative in-place removal approach, which eliminates the need for extra memory. Instead of creating a new list, we modify the existing list by relinging the next pointers of nodes, effectively skipping over any nodes with the target value val. To simplify edge cases, such as when the head of the list needs to be removed, we introduce a dummy node that points to the head of the list. Using a pointer, we traverse the list starting from the dummy node. At each step, we check if the value of the next node matches val. If it does, we adjust the next pointer to skip the node. Otherwise, we move the pointer forward and continue until the end of the list. After completing this process, the dummy node's next pointer will point to the updated head of the list, which we return as the result. This approach is highly efficient, operating in time and O1 space, but it requires careful handling of edge cases and the dummy node. Another method to consider is the recursive solution, which simplifies the logic by reducing the problem into smaller subproblems. Here, the idea is to process the rest of the list recursively and decide whether to include the current node in the final result. If the head of the list is null, we've reached the base case, and we simply return null. Otherwise, we recursively process the next node and determine whether the current node's value matches val. If it does, we skip the node by returning the result of the recursive call. If not, we link the current node to the recursive result and return the current node as part of the updated list. While this approach is elegant and intuitive, it has a major drawback: it requires O(n) space for the recursive call stack, which can lead to stack overflow for very large lists. This makes the recursive method less practical for inputs with a significant number of nodes. Given the trade-offs of each approach, the iterative in-place removal strategy stands out as the optimal solution for this problem. It is both time-efficient, with a complexity of O(n), and space-efficient, requiring only a constant amount of additional memory. The use of a dummy node simplifies edge cases, such as removing the head of the list or handling an empty list, making the implementation robust and reliable. While the recursive approach is elegant, its high space complexity and risk of stack overflow make it unsuitable for large inputs. Similarly, the brute force method of rebuilding the list is unnecessarily memory-intensive compared to the in-place modification. Overall, the iterative strategy meets all the problem's constraints, handles edge cases effectively, and avoids unnecessary overhead, making it the clear choice for solving this problem. In this problem, we need to remove all nodes from a singly linked list that contain a specified value, val. The solution involves modifying the list in place and returning the updated head. To achieve this, we start by creating a dummy node. This dummy node is a new node whose next pointer is set to the head of the input list. The purpose of this dummy node is to simplify edge cases, such as when the head node itself needs to be removed. It acts as a placeholder so that we never lose the reference to the new head of the list after modifying it. Next, we set up a pointer called current, which initially points to the dummy node. This pointer will allow us to traverse through the list while making any necessary modifications. The algorithm proceeds by traversing the linked list using the current pointer. While the current.next pointer is not null, meaning there are still nodes left to process, we check if the value of the next node, current.next.val, matches the target value val. If it does, we adjust the next pointer of the current node to skip over the node with the matching value. This effectively removes the node from the list. If the value does not match, we simply move the current pointer to the next node to continue the traversal. Once we've processed all nodes in the list, we return dummy.next as the new head of the list. This ensures that the dummy node itself is excluded from the result, and the updated list is returned correctly. There are several key insights to note about this algorithm. First, the use of a dummy node is crucial because it simplifies the logic for handling edge cases, such as when the head node needs to be removed or when the list is empty. Second, the algorithm modifies the next pointers directly, which allows us to perform the operation in place, achieving a space complexity of O(1). Finally, since each node in the list is visited exactly once during the traversal, the algorithm has a time complexity of O(n), where n is the number of nodes in the list. The problem operates on a singly linked list, which only allows for one-directional traversal. By adjusting the next pointers, we can efficiently modify the list without requiring additional data structures. The dummy node is a key part of this design and simplifies handling both normal cases and edge cases. The algorithm also handles several important edge cases effectively. If the input list is empty, or the head is null, the algorithm will simply return null, as there are no nodes to process. If all nodes in the list contain the value val, the algorithm will remove every node, resulting in an empty list. Conversely, if none of the nodes contain the value val, the list remains unchanged. For a list with only a single node, the algorithm will either remove the node if it matches val or leave it unchanged if it does not. In terms of complexity, the time complexity remains O(n), because each node is visited exactly once, and the space complexity is O(1), as no additional data structures are used beyond the dummy node. To better understand how the algorithm works, let's walk through an example. Suppose the input linked list is 1-2-6-3-4-5-6, and the target value val is 6. We start by creating a dummy node that points to the head of the list, resulting in dummy-1-2-6-3-4-5-6. We initialize current to point to the dummy node. As we traverse the list, we first encounter the node with value 1. Since it does not match val, we move current to the next node. The same happens for the node with value 2. When we reach the node with value 6, it matches val, so we remove it by updating current.next to skip over this node. We continue this process for the rest of the list, removing all nodes with the value 6. At the end, we return dummy.next, which gives us the updated list, 1-2-3-4-5. This implementation solves LeetCode problem 203, remove linked list elements, by iterating through the linked list and removing nodes with a specified value. The list node class defines the structure of a node in the linked list. The solution class contains the remove elements method, which performs the removal operations. The algorithm starts by creating a dummy node with an arbitrary value, -1, and points its next to the head of the list. This dummy node simplifies edge cases like removing the head node itself. Two pointers, previous and cur, are initialized. Previous starts as the dummy node, and cur starts as the head of the list. The loop iterates through the linked list using cur. Inside the loop, if the value of the current node matches the target value val, the prev next pointer is updated to skip the current node, effectively removing it. Otherwise, previous moves forward to the current node. In either case, cur always advances to the next node. After the loop ends, the function returns dummy.next, which points to the new head of the modified list. This approach ensures that all occurrences of val are removed while handling edge cases like an empty list, nodes with repeated values, or removing the head node directly. The algorithm runs in O(n) time, where n is the number of nodes in the list, as it traverses the list once. The space complexity is O(1), since no additional data structures are used apart from the dummy node. Here, we begin by defining our solution class, which includes the definition for the list node class to represent nodes in a singly linked list. Each node contains an integer value and a reference to the next node. We also define several constructors to initialize a node with no parameters, with just a value, or with both a value and a reference to the next node. Now, in the remove elements method, we start by creating a dummy node. This dummy node is initialized with a placeholder value of -1 and points to the head of the original list. Using a dummy node helps simplify edge cases, such as when the head node itself needs to be removed. Next, we initialize two pointers, previous and cur. The previous pointer starts at the dummy node, while cur begins at the head of the list. These pointers will help us traverse the list and manage node removal. To traverse the list, we use a while loop that continues as long as the cur pointer isn't null. Inside the loop, we check if the value of the current node matches the target value val that needs to be removed. If it does, we adjust the previous pointer's next reference to skip the current node, effectively removing it from the list. If the current node's value does not match val, we simply move the previous pointer forward to the current node. Regardless of whether a deletion occurs, the cur pointer is always advanced to the next node in the list to continue the traversal. Once the loop finishes, we return dummy.next, which points to the new head of the modified list. This approach ensures that all nodes with the specified value are removed while maintaining the correct structure of the linked list. To solve the problem of removing all nodes with a specific value from a linked list, we start with an example where the input list is 1-2-6-3-4-5-6, and the value to remove is 6. First, we create a dummy node with a value of -1, which serves as a placeholder to simplify edge cases like removing the head node. This dummy node points to the head of the linked list. We then initialize two pointers, previous, starting at the dummy node, and cur, starting at the head of the list. Now, as we iterate through the list, the first node has a value of 1, which is not equal to 6, so we simply move both pointers forward. Next, the node has a value of 2, which again is not equal to 6, so we move our pointers forward once more. When we reach the third node with a value of 6, we remove it by updating the next pointer of the previous node to skip over cur. This effectively removes the node with value 6 from the list. We then continue processing the subsequent nodes, moving forward as long as their values are not equal to 6. Eventually, we reach the final node with another value of 6, and we remove it in the same way, updating prev next to skip it. At this point, the list is fully processed, and we are left with 1-2-3-4-5. After removing the last node with a value of 6, the cur pointer becomes none, indicating we have reached the end of the list. The resulting linked list is now 1-2-3-4-5. Let's move on to another example to understand how this method handles cases where every node in the list matches the value to be removed. In this case, the input list is 1-1-1 and the value to remove is 1. Similar to before, we create a dummy node with a value of -1 that points to the head of the list, and we initialize the previous and cur pointers. This setup ensures that even if all nodes are removed, we still have a valid starting point to return the resulting list. We begin iterating through the list where every node has the value 1. For the first node, since cur.val equals 1, we remove it by updating prevNext to point to cur.next, effectively skipping over the node. The previous pointer remains unchanged, while cur moves forward to the next node. This process is repeated for the second and third nodes, both of which also have the value 1. Each time, we update prevNext to skip the current node and move cur forward. After processing all nodes, cur becomes none, and the list is now empty. The final output for this example is an empty list, represented as. Finally, let's examine a scenario where the target value does not exist in the list. The input list is 2-3-4, and the value to remove is 7. As before, we start by creating a dummy node pointing to the head of the list and initializing our previous and cur pointers. As we traverse the list, we find that none of the nodes have a value equal to 7. For each node with values 2, 3, and 4, we simply move both pointers forward without making any changes. Eventually, cur becomes none, indicating the end of the list. Since no nodes were removed, the final output remains 2-3-4. This demonstrates that the solution correctly handles cases where no nodes match the target value. The time complexity of this solution is O(n), where n represents the number of nodes in the linked list. This is because the algorithm processes each node exactly once, iterating through the entire list using a while loop. During each iteration, it performs constant time operations, such as checking the value of the current node, updating pointers, and moving to the next node. Since these operations are independent of the size of the list, they each have a time complexity of O(1). When you combine this with the fact that there are n nodes to process, the total time complexity becomes O(n). This holds true for all scenarios. In the best case, when no nodes match the target value, the algorithm still needs to traverse all n nodes. In the average case, when only a subset of nodes matches the target, it still processes every node, and in the worst case, when every node matches the target value, the algorithm again iterates through all n nodes. Thus, regardless of the input, the time complexity remains O(n). Now, let's look at the space complexity, which is O(1). This means the algorithm uses a constant amount of extra memory, no matter how large the input linked list is. The key here is that it operates directly on the input list, modifying it in place without allocating additional data structures like arrays or stacks. The only extra memory required is for 3 pointers, dummy, previous, and cur, which are used to traverse and modify the list. Since the memory used by these pointers does not grow with the size of the input, the space complexity remains constant, or O(1). This efficiency is a significant advantage, as it ensures minimal resource usage while solving the problem. To put this into perspective, let's compare it to a brute force or naive approach. A naive solution might involve creating a new linked list to store nodes that do not match the target value. While this approach would work, it introduces additional space requirements proportional to the number of nodes in the list, resulting in a space complexity of O(n). In contrast, the current solution avoids this overhead by modifying the input list in place, making it far more space efficient. Additionally, it achieves the optimal time complexity of O(n), which is the best possible for this problem, as every node in the list needs to be checked at least once. These advantages make the current solution both time and space optimal. Finally, let's justify these complexities mathematically. For time complexity, the while loop runs n iterations, one for each node in the list. Since each iteration involves constant time operations, the total time complexity is the product of O(n) iterations and O(1) operations per iteration, resulting in O(n). For space complexity, the memory usage is dominated by the 3 pointers, dummy, previous, and cur, which are fixed in number and do not depend on the size of the input. This means the space complexity is O(1). In conclusion, this solution is both time and space efficient, achieving O(n) time complexity and O(1) space complexity. it handles all cases, whether best, average, or worst, by directly modifying the input list in place and iterating through it exactly once, making it an optimal and elegant solution to the problem. When tackling this problem, there are a few common mistakes to watch out for. First, failing to update the head pointer can cause critical errors. If the head node itself contains the target value, you need to carefully move the head pointer to the next valid node after removing it. Forgetting this step means your list will still start with the node that should have been removed. Second, skipping nodes after removal is another frequent issue. When you remove a node, the pointer to the next node must be updated correctly, otherwise, you might inadvertently skip over other nodes that also need to be checked for removal. Third, modifying the list without using a dummy node can make handling edge cases, like removing the head node, unnecessarily tricky. A dummy node simplifies pointer management and reduces the likelihood of errors. Another pitfall to avoid is infinite loops, which can occur if the while loop isn't properly managed. Always ensure that the current pointer is advanced correctly, even when removing nodes. Lastly, don't overlook edge cases like empty lists or single node lists where the node's value matches the target. These scenarios are easy to miss in testing but can break your solution if not handled properly. Now, from an interview perspective, this problem is often used to assess your understanding of pointer manipulation in linked lists. It's critical to show that you can manage the current pointer and its current .next reference while iterating through the list. Optimization is another area of focus. While the standard solution operates in O(n) time, interviewers are just as interested in your ability to write clean, bug-free code as they are in efficiency. Be prepared to discuss edge cases thoroughly. Situations like lists where all nodes contain the target value or where the target value doesn't exist at all are common follow-up questions. Another topic interviewers might explore is the trade-off between using a dummy node and modifying the head pointer directly. Dummy nodes simplify the logic and reduce the chance of errors, but they do come with a slight overhead. Understanding these trade-offs and articulating your reasoning can help you stand out. Finally, let's connect this problem to related ones and alternative approaches. If you're looking to strengthen your understanding of linked lists, consider tackling problems like LeetCode number 206, which involves reversing a linked list, or number 83, where you remove duplicates from a sorted list. Both require precise pointer updates. Other good practice problems include number 21, merging two sorted lists while maintaining proper pointer management, and number 234, which tests operations like reversing and comparing linked lists for palindromes. Now, when it comes to alternative approaches, the iterative solution with a dummy node is the most common due to its simplicity and robustness. It has a time complexity of O(n) and uses O(1) space. A recursive solution, on the other hand, can be more elegant since it processes the rest of the list first before deciding whether to include the current node. However, recursion risks stack overflow for very deep lists and has a space complexity of O(n) due to the recursion stack. Lastly, directly modifying the head pointer without a dummy node can save some space but makes the code more complex and prone to bugs, especially in edge cases. Choose the approach that balances clarity and efficiency for your specific use case. Great job! We've successfully solved LeetCode problem number 203 by efficiently removing nodes with a specific value from a linked list. Remember the importance of dummy nodes for handling edge cases and the value of in-place solutions to optimize space. Thanks for watching, and don't forget to like and subscribe for more problem-solving tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!